Hi, welcome to LMS Solution. Today we are going to see about how to mitigate power quality. That means how to improve the power quality of the power system. Okay, so for that, so I have created one Simulink model. Okay, so that means this is consist of three-phase voltage source. So I'm going to open that model. Okay, so it is a three-phase grid or three-phase voltage source, and it face-to-face voltage is 500 kilovolt, and then operating frequency is 60 hertz, and then source inductance is around 98.03 millihenry. Okay, and then I'm going to use some parallel elements, resistance, inductance, in series with that source. So here I am considering resistance is 26.07 and inductance is 48.86 millihenry. So this is nothing but resistance and inductance of that line. Okay, so here we are going to measure the voltage for that main face to ground, line to ground voltage, and then current through that three-phase line. So this is going to be considered as bus 1. So here also we are going to measure that voltage and current, and then this measurement is going to be considered as a bus 2. Okay, here we are going to measure three-phase voltage VABC, three-phase current IABC, and then here they are mentioned it as a bus 2. Okay, so here we are measuring a three-phase voltage and three-phase current, and here the bus is mentioned as a B1. Okay, so in between the bus B1, B2, we are going to connect the harmonic filter. So that means single tuned, double tuned, high pass and C-type high pass harmonic filter. So after bus 2, right, here I am going to connect that transformer. That means step down transformer. So the transformer rating is 1200 MVA. Okay, and then input voltage is 500 kilovolt, the output voltage is 200 kilovolt. Okay, so here we are using 3 winding transformer. So winding 2 and winding 3 has voltage of 200 kilovolt. Okay, and then output of the transformer is going to be connected with the rectifier. So here the rectifier, cascade rectifier is used here in order to connect. That means this rectifier going to be act as a non-linear load. So in order to create that so here we are using two rectifier connected cascade, and this rectifier and load going to be act as a non-linear load in order to create that power quality problem in the power system. So here we are going to connect that load. Okay, so this is a load. That means 1000 megawatt load is connected here, and then we are going to control this rectifier by using this pulse generator. Okay, so this is pulse generator. So this is 12 pulse generator, and then pulse width of that generator will be 40 degree. Okay, and then that triggering angle is here I'm going to consider 90 degree. Okay, so here we need to provide another value, nothing but omega t. So the omega t is going to be generated based upon bus 1 voltage. Okay, so here we are going to measure that bus voltage VABCP1, right? So by using that VABCP1 we are going to generate that omega t. Okay, so these are the input, that omega t and the alpha value is input for that pulse generator. So it going to be generated 12 pulse. Okay, so that pulse going to be given to rectifier. It going to be control the input AC voltage and it going to be converted into DC. Okay, and then here I'm going to connect that main harmonic filters. Okay, so in between bus 1 bus 2, see here I'm connected that harmonic filter, single tuned, double tuned, high pass and C typed high pass filter. Okay, and then you can enable so each and every harmonic filter by means of this selector switch. Okay, so this is a manual switch, so we can enable and disable that each harmonic filter. Okay, if you make that position of that manual switch in downside means it going to be connect to 0, that mean that circuit breaker will be in open condition. If you change that position to top right, so this will be connected to 1, then that circuit breaker going to be close condition. Okay, that means that harmonic filter going to be connected to the system to mitigate some power quality. That means it going to be improve the power quality of the power system. Okay, so initially I'm going to make all switch position to 0. Okay, here you can see that the switch position is 0, here switch position is 0, here switch position 0 and 0. Okay, and then I'm going to simulate this model and then I'm going to see the waveform of that bus B1 B2 voltage and current. Okay, so I'm going to simulate this one. So you can see that, so this is the bus B1 and bus voltage of voltage of the bus B1 and current of the bus B1. So this is the current of the bus B2. Okay, so here you can see that the voltage response very not sinusoidal, it have some distortion, right? And also current also not sinusoidal, it has some distortion. Okay, so next we need to measure the THD value. Okay, so for that go to configuration parameter, go to login. Okay, already we store the data as scope on. Okay, so first we need to check the THD of the bus, that means voltage of the bus B1 and the current of the bus B1. Okay, so we need to check that one. Okay, so our objective is to mitigate the power quality in the bus B1, that means in source side. So we need to make that source voltage near to sinusoidal. Okay, and then current of the source is near to sinusoidal. Okay, so here this is nature of that source voltage and current, that means bus 1 voltage and bus 1 current is a source voltage and current. Okay, so next we need to check the THD. So for that go to this block discrete. Okay, so discrete block and then click tools and then go to FFT analysis. So it will open another window. Okay, so this is voltage. Okay, so phase, that means A phase. Okay, so next you can click FFT window. So here I'm going to mention the starting time will be 0.06 and I'm going to consider number of cycle equal to 1. Okay, and fundamental frequency is 60, and the maximum frequency of that harmonic order will be, that means harmonic frequency will be 4000. And then I'm going to make just to make this as same as maximum frequency. So after clicking that one, just to click this one, display. So here you can see that the THD of that voltage will be 16.86%. Okay, so next you just you have to go to, just to open some Excel and then note down the reading. Okay, so I'm going to go to Excel to note down the reading of that voltage and current without any harmonic filter. So here I'm going to mention THD of power system, okay, without filters. Okay, so here VA, VB, sorry, VB and VC. Okay, and then here IA, IB and IC. Here I'm going to measure THD. Okay, so here you can see that THD value is around 16.86. okay, so here I'm going to mention 16.86. next I'm going to measure the THD of the second signal. Okay, once again I'm going to click FFD window and then see the percentage. So here 16.83. okay, 16.83. and for third signal, that one third voltage signal. Okay, so 16.85. okay, 16.85. so here you can see that 16.85. so next I'm going to measure the THD for a current of the bus 1. Okay, here the current THD will be 7.39. okay, 7.39 for phase A. For phase B, 7.35. okay, 7.35. and then for phase 3, okay, the THD is 7.36. 7.36. so you can see that a different value. That means if you want to see the details, for example, so here you can see that, right, this harmonic level is very high, this point, this one, and this one, this one, this one. okay, but you can see that this harmonic level is very high, so you can draw that with the harmonic order. okay, and also you can see the list relevant to fundamental, list relevant to basic base. okay, so this, so here you can see that the 11th harmonic and the 13th harmonic having highest value. okay, but the remaining things will be very less when compared to fundamental. okay, this is fundamental. Compared to that fundamental, the value of the other harmonic odd harmonic H3, H5, H7, H9 will be very less, but you can see that the harmonic of 23, okay, and then 13 and then 11, so it is very high. okay, Next I'm going to see that list of fundamental. Okay. Yeah, so list around fundamental. So it's showing the percentage of the THD variation. So here also you can easily find out the harmonic content for the 11th order will be 5.96 percentage, for 13 will be 4.12 percentage, then okay, so remaining will be very low, right? Not much high. Okay, but when considering 11 and 13, so both are having highest harmonic level, so that's why we are getting that harmonic of 7.36 percentage. So I'm going to check with second signal. Here also you can see that 11 and 13 will be very high. For first signal also, current signal. Okay, let's say 11 and 13 having highest percentage of harmonic level. Okay, so for voltage you have to check. For voltage also that 11 and 13 having highest value. Okay, and then 23 also having highest value. Okay, so that's why we are getting this kind of that means 16 total harmonic around 16.86 percentage. For second signal, here 12.16, 11th harmonic is 12.16, so 12.16, and then 13 will be 9.84 percentage, and then 23rd harmonic will be 3.87 percentage. Okay, so this is the THD value, total harmonic distortion, and see individual harmonic of that voltage and current. Okay, so without compensation or without harmonic filter. So this is because of this non-linear load. Okay, here we are using rectifier with some resistive load, so this going to be act as a non-linear load. Because of this non-linear load, so input voltage and current quality is affected in this system. That means input voltage THD is around 16.8, and then input current THD is around 7.3. Okay, so next we need to use some harmonic filter. So by using that harmonic filter, how we are going to improve that that means improve the power quality of the voltage and current. Okay, so first I'm going to use single tuned harmonic filter. So this is the block for single tuned harmonic filter. So I'm going to on that single tuned harmonic filter by changing the switch position. Okay, so this is setting of the single tuned harmonic filter. That means it's going to be connected in between bus 1 bus 2, so that voltage will be 500 kilovolt, frequency will be 60, and then I'm going to take nominal reactive power is 150 megawatt, and then I'm going to consider tuning frequency. Okay, for example, so 11th harmonic need to be minimized, so I'm going to fix 11 here, and then we will check the THD value of that 11th harmonic in the current and voltage. Here I'm going to fix the quality factor is equal to 7. Okay, then apply and then okay. Next I'm going to simulate this same model, and then we will now you see that variation of that voltage and current in the bus 1 bus 2 and the bus 1 bus 2. Okay, now simulating this one, you will see some variation because of that single tuned harmonic filter. Now you can see that, so there will be changes in the yellow color waveform and the blue color waveform, but in red color we will not get effect. Okay, that means because of adding that single tuned harmonic filter, so we can make that yellow and blue phase going to be change that nature. That means the THD value going to be reduced, but when comparing then the red one, right, is not changing the nature. So next we have to check that THD of that different um, values. Okay, I'm going to refresh. Okay, so here we are going to measure that voltage THD of bus 1. Here I'm going to measure the first signal voltage, that means for R phase. Okay, here you can see that the TH2 will be 1.47 percentage. I'm going to change the display level. Okay, you will get idea. Okay, here 1.47 percentage, but here this single tuned harmonic filter is connected to the system. So because of that single tuned harmonic filter, the TH2 will reduced to 1.43 for in phase A. Okay, so next I'm going to check this one. Surface B, the TH2 value is 2.46 percentage, and I'm going to check that phase C. Okay, here 14.91, so it will be not reduced, right? Only 2 percentage, around 1.5 percentage only reduced. Okay, because of that single tuned harmonic filter. That means so you will see that the large reduction in TH in the phase A and B, but the one only around 1 point, I think 2 percentage or 1.8 percentage reduction in that phase C because of that single tuned harmonic filter. So next we have to check that harmonic content of bus 1 current, that means harmonic content in the current in the bus 1. Okay, so this is for phase A current, so it's around 1.02. Okay, 1.02, and then for phase B, so it's around 1.16 percentage, and then for phase C, this is around 6.6 percentage, 6.64 percentage. So because of that single tuned harmonic filter, so we can able to reduce the THD in phase A and B, but not able to reduce the harmonic content in the phase C. Okay, next we will check that the individual harmonic details. Okay, so here you can see that that when this phase C, okay, I'm going to change that to phase A. So you will see that because of that single tuned harmonic filter, we will able to reduce the THD. Okay, of that means 11th harmonic, 13th harmonic is reduced to some level. Okay, because of that the total harmonic going to be reduced from 7.3 percentage to 1.02 percentage. Okay, so this is a variation of that single, that means THD variation of phase A, B, C in voltage and current because of that single tuned harmonic filter. So next I'm going to change this one. Okay, I'm going to turn off that single tuned harmonic filter. Next I'm going to enable that double tuned harmonic filter. Okay, that means I'm going to change the switch position from 0 to 1. So this is a parameter detail in the double tuned harmonic filter. So this is line voltage and frequency, and I am going to consider 150 megawatt reactive power, and then tuning frequency. So already we see that right 11th and 13th having some highest level of percentage. Okay, that means THD is very high for 11th and 13th harmonic. Okay, so that's why we are going to take two frequency. One is 11th harmonic frequency, another one is 13th harmonic frequency. Once again, I'm going to make quality factor equal to 7 and then apply and okay. So next I'm going to simulate this same model. Yeah. So because of double tuned harmonic filter, right? So we'll see that some that mean quality of that voltage and current is increased. Okay, in this system. Okay, so you can see that the voltage is nearer to sinusoidal. Current also is nearer to sinusoidal in the plus one. Okay, so next we have to check the THD. So because of the double tuned harmonic filter, the THD will be 1.74. So double tuned harmonic filter, and then for phase A is 1.8, for phase C, okay, is around 1.83, for current harmonic. Okay, for phase A is 0.53, for phase B is 0.7, 2.7, and phase C is around 0.76. Okay, so here you can see that because of the double tuned harmonic filter, right, I think the 11th and 13th fully removed in the power system voltage and current. Okay, so that's why we are having this kind of THD 1.7, 1.8, 1.83, and 0.53 and 0.57, 0.76. Okay, so when compared to that single tuned, right, here that is phase C voltage and current not reduced, right, because of that single tuned harmonic filter, but because of double tuned, right, the all phases voltage and current, okay, the TH will be reduced very effectively because of the double tuned harmonic filter. Okay, and also we can check that individual harmonic level. So here you can see that you check that 11th and 13th harmonic is almost vanished, right? So because of that only we are getting this kind of TH 0.76%. Okay, so next I'm going to change that harmonic filter. That means I'm going to change that harmonic filter to high pass filter. Okay, I'm going to enable that high pass filter. So for that I'm going to change the choose position from 0 to 1. Next we have to check the response of that system. So this is a response of that system. So before that I'm going to show that high pass filter detail. Okay, here high pass, here line to line voltage is 500 kilovolt, 60 hertz, same 150 megawatt. Okay, here I'm going to take tune to frequency equal to 11. Okay, and then I'm going to make quality factor equal to 7 and then apply, then okay, and then once again I'm going to simulate the same system. So you will see that variation. Yeah. So here you can see that this responses look like a single tuned harmonic filter response, right? When you add single tuned harmonic filter in the system, the phase A and B have some better response. That means the power quality level is improved, but in phase C, right? So you will not get that means the THD not improved at, as much. Okay, so next you have to check that THD value. So this is voltage of that phase A. So next you need to check that THD. So here THD is 1.39. Okay, so high pass harmonic filter, because of high pass harmonic filter, the phase A THD will be 1.39, and then for phase B the harmonic THD, that means total harmonic distortion, is 2.35, and then for phase C the THD will be 14.87. okay, sorry, 14.87. So next you have to check the THD of the current. For phase A the THD is 1.08, and then phase B the THD is 1.18, and then phase C the THD is 6.62. okay, so this is the THD after including that high pass harmonic filter in the system. So that harmonic THD, that means THD of that system under that high pass filter, so is same like that single tuned harmonic filter. Okay, both are having some similar response. Okay, so next I'm going to move on to that C type high pass filter. So for that I'm going to disconnect that high pass harmonic filter. I'm going to connect C type high pass filter, and then I'm going to open that C type high pass filter. So this is a rating of that C type high pass filter. So here I'm going to initialize that line to line voltage is 500 kilovolt, 60 Hz frequency, 150 megawatt active power, and then I'm going to make tuning frequency is 11, and then quality factor equal to 7. okay, and then I'm going to apply, and then I'm going to submit the model. Because of that C type high pass filter, so we'll check the response. Now you can see that because of C type high pass filter, you can see the voltage response and current response. That means both are having some near sinusoidal waveform, right? That means THD is reduced in the system. Next you have to check the THD of that voltage and current. So this is phase A voltage. I'm going to see that THD value, it is 2.17. so C type harmonic filter, so this the 2.17. okay, 2.17. For phase B harmonic level is 2.23, and phase C the harmonic level is 2.24. Next you have to check the harmonic for current. For phase A is 0.77, because of the next current at phase B is 0.88, and then current in the phase C is 0.93. Okay, so because of that C type high pass harmonic filter, the THD is so much reduced from the without filter concept, right? When comparing this value to this value, this will reduced much, right? That mean you can comparing that one, that then we can compare this C type with double tuned harmonic filter, because the double tuned C type going to be reduce the THD in all phases A, B, C. Okay, but in case of single tuned and high pass harmonic filter is not reduce the THD in the phase C. Okay, so finally I'm going to take this 2 1, right, and comparing that value of THD in double tuned and C type harmonic filter. Double tuned harmonic filter has less THD value in the voltage and current. So from that finally I conclude the double tuned harmonic filter has a better response in the power system to reduce the THD in the voltage and current. That means it improve the power quality in the source current and voltage. Thank you.